Hello ladies and gentlemen, welcome back to our session. Today I am going to explain you few concepts related to semiconductors. First of all, what is a semiconductor? Semiconductor is a material whose conductivity lies between insulators and conductors. Here the best examples of semiconductors are germanium and silicon. Here we have two different types of semiconductors, intrinsic semiconductors and extrinsic semiconductors. Again, these extrinsic semiconductors are divided into N-type semiconductors and P-type semiconductors. While coming to the concept of intrinsic semiconductors is nothing but pure form of semiconductor. The best example for these intrinsic semiconductors are pure silicon and pure germanium. Here at room temperature, the number of electrons are equal to number of holes in intrinsic semiconductors. This figure shows the best example of intrinsic semiconductor, which is having one free electron, which is useful to form electron hole pair in bonding. While coming to energy band diagram of intrinsic semiconductors, here we have valence band, conduction band and Fermi level. Here electrons always will try to jump from valence band to conduction band after gaining some energy. While coming to extrinsic semiconductor, here we can see that addition of impurities to the pure form of semiconductor will get an extrinsic semiconductor. The process of addition of these impurities to the pure form of semiconductor, we are calling it as doping. Here in extrinsic semiconductors, without breaking the covalent bonds, we can increase the charge carriers. Here we have some points related to the comparison of intrinsic and extrinsic semiconductors. While coming to N-type and P-type semiconductors, we have few comparisons. Here N-type semiconductors having pentavalent impurities and P-type having trivalent impurities. Majority carriers are electrons and majority carriers are holes in P-type. Likewise, we have different comparisons between N-type and P-type semiconductors. First of all, we are going to learn about N-type semiconductors. When we have adding pentavalent impurities to your pure semiconductor, we will get N-type. Here I am taking pure silicon and I have taken arsenic as impurity. Now I am adding arsenic to the pure silicon to form N-type semiconductor. This is the way your N-type semiconductor will be formed. Here arsenic atom having 5 valence electrons, the 5th electron is superfluous and becomes free electron and enters into conduction band. Therefore, pentavalent impurities are donating 1 electron and they are becoming positive donor ion. So we can call pentavalent impurity as a donor. While coming to P-type semiconductors, here we are adding trivalent impurities to the pure silicon to get here P-type semiconductor. The best examples here I have taken are gallium and pure silicon. This is the way your P-type semiconductor is going to form. And this P-type semiconductor, gallium atom having 3 valence electrons and it makes a covalent bond with adjacent 3 free silicon atoms. But we have one more free electron in silicon to form a covalent bond. Because of the deficiency of the electron in the gallium atom, we will getting one hole here. So in P-type semiconductors, we have majority carriers are holes. Now, this is the P and N-type semiconductors, and here the acceptor ions in P-type and minority are electrons, majority are holes. These figures shows P and N-type semiconductors with majority and minority charge carriers and acceptor and donor ions. And already we have gone through these differences previously. Now I am moving on to conduction here. Conduction in semiconductors will be carried out by two different processes, drift process and diffusion process. While coming to drift process, this figure shows the continuous movement of electrons and holes in semiconductor device. Here electrons move from external circuit and in conduction band of the semiconductors. Holes move in valence band of the semiconductor. This is the process of drift. While coming to diffusion process, moving of electrons from higher concentration gradient to lower concentration gradient is also known as diffusion process. Here P and N type semiconductors are shown in here. How PN junction will be formed? Here the basic diode we are going to learn in semiconductor devices is PN junction diode. Here with the help of external supply voltage, here these are the holes and these are the electrons. The minority carriers in N-type semiconductors are holes. The minority carriers in P-type semiconductors are electrons. With the help of external supply voltage to your P-N diode, what is going to happen? The electrons and holes are attracted towards each other and they will try to cross the barrier to form electron-hole pair. This is the process is going to happen to form the depletion region. And this is the formation of P-N diode. Here a P-N junction diode is formed if donor impurities are introduced into one side and acceptor impurities are introduced onto other side of a single crystal of semiconductor. Initially there are P-type carriers to the left side of the junction and N-type carriers to the right side of the junction as shown in the figure. On formation of P-N junction, electrons from N side and holes from P side diffuse towards the junction and the recombination takes place at the junction. With the recombination, here immobile positive donor ions at N side and negative acceptor ions at P side will exist. Here, while coming to another point, potential barrier develops at the junction whose voltage is 0.3 volts for germanium and 0.7 volts for silicon. The further diffusion stops and results in a depletion region at the junction. Here, what is a depletion region? Since the region of the junction is depleted of mobile charge carriers, it is called a depletion region or space charge region or transition region. Here the thickness of the region is of order of 0.5 micrometers. Here this symbol shows the circuit of your PN junction diode. The positive side is represented with A, it is anode, and negative side is represented with K, cathode. Arrowhead indicates the direction of conventional current flow here. Here while coming to the working of PN junction diode, we have three different modes of operation. First one is no application of voltage. Second one is forward biased condition. Third one is reverse biased condition. Now we are discussing about forward biased condition. Here we have taken silicon semiconductor material for the formation of PN junction diode, and the positive terminal of the diode is connected with the P type of silicon and negative type of terminal is connected to the negative terminal. This is the circuit in forward bias condition. Here the figure shows how the electrons and holes will recombine at the junction with the application of forward voltage. Here with the application of forward voltage with the help of external battery, the electrons present in the N type and the holes present in the P type are attracted towards each other. They will try to cross the potential barrier to form electron hole pairs. Because of the movement of this electrons, we will get highest amount of current flowing through your PN junction diode when it is connected in forward bias condition. While coming to forward bias, the majority charge carriers driven towards the junction, and this is the result in the reduction of the depletion region and the width of the potential barrier. As the applied bias steadily increased from 0 onwards, the majority charge carriers attempts to cross the junction. Holes and from P side flow across the negative terminal on the N side, and electrons from N side flows across to the positive terminal on the P side. Here, the device simply behaves as a low resistance path when it is connected in forward bias condition. Here, what are the different features when the diode is connected in forward bias condition? Here, the diode can act as a low resistor, and the current is mainly due to the flow of majority charge carriers across the junction, and the potential barrier and the depletion layer is reduced. Now, we are discussing about when the diode is connected in reverse bias condition. Here, in reverse bias mode, positive terminal of the diode is connected to negative terminal of the battery, and N-type material to the positive terminal of the battery. Here, under reverse bias condition, opposite polarities always attracted towards each other. We know the same principle work here. The majority carriers in the holes are attracted towards the negative terminal of the battery, and the majority electrons present in the N-type are attracted towards the positive terminal of the battery. Because of this, what will happen? Our depletion width will goes on increasing in reverse bias condition. If the depletion width is more, means there is no chance of movement of charge carriers from N-type to P-type or from P-type to N-type. So, ideal case, what we can see, when the diode is connected in reverse bias condition, the amount of current flow flowing through the diode is 0. Here, external bias voltage applied is positive terminal on N side and negative on P side. Here, these are the points related to the PN junction diode connected in reverse bias condition. This is the energy band diagram. Here, what are the different properties of PN junction diode? The junction contains immobile ions, that is, this region we will call it as depleted of mobile charges. This region we will call it as depletion region, space charge region, or transition region. The width of this transition region is 1 micron. The cut-in voltage of diode is 0.3 volts for germanium and 0.6 volts for silicon. Here, the reverse saturation current doubles for every 10 degrees rise in temperature. Forward resistance is of the order of ohms, and the reverse resistance is in the order of mega ohms. The transition region increases with the reverse bias. This region also considered as variable capacitor and also known as transition capacitance. This figure shows the VI characteristics of PN junction diode when it is in forward bias condition and in reverse bias condition. Here, with a gradual increase of voltage from 0 to 30 volts, we can observe that along with the supply voltage, the current is also increasing linearly when the diode is connected in forward bias condition. When the diode is connected in reverse bias condition, the amount of current flow is always constant. This is the diode current equation. I equal to I naught into e power v by eta vt minus 1. Here, I naught is the reverse saturation current and vt is the threshold voltage or thermal voltage, and eta is the ideality factor. Here, this figure shows the graphical representation of diode connected in forward bias condition. So, here the voltage increase voltage increases means current also increases in forward bias, and in reverse bias goes on increasing the supply voltage. Here voltage is constant. At sudden breakdown voltage it will be constant. This is the diode equation. Eta is the ideality factor, and this value will vary, depends on the semiconductor material what we have used for the preparation of PN junction diode. That's all for today's class, friends. Tomorrow again we will discuss about the remaining concepts. Thank you so much. Thank you all.